Okay, hello everyone. Welcome to another episode of Science and Technology Q&A for kids and others. Sorry I missed last week. I was close to being able to do it, but I was traveling and the technology didn't quite work. All right, well, let's see. I'm happy to try and address all kinds of questions about elementary, not so elementary science, technology, whatever. We seem to have a bunch of questions left over, and let me try and see if I can address a few of these. So there was a question here. I'm always suspicious of questions which seem like they're easy because I'm not. As I get into these, I sometimes realize, oh gosh, there's this thing that seems obvious to me, but actually it's not quite so obvious. But so here's one that it's about how do induction cooktops work without burning your hand if you touch them, and that's also similar to questions about how wireless charging of phones and other such things work. Okay, so the big idea is this phenomenon called electromagnetic induction, which was discovered by Michael Faraday back in the 1800s. And here's the thing, and it's a sort of fundamental fact. It's that magnetic fields can now, you see, this is, I knew, as I got into this, I knew that that we'd have issues here. But the basic story here is changing magnetic fields can induce electric currents, and the basic idea is when you have a changing magnetic field, you can you end up being able. So what's actually happening? What's happening? See now that I shouldn't have. I jinxed this by even saying that questions that seem easy often aren't. The sort of fundamental physics of it is the physics of the electromagnetic field, governed by these things called Maxwell's equations. And I'm kind of now thinking through, there's this equation that says curl B equals a current. And that's the equation. Let's think about this for a second. I'm now, yeah, this is terrible. Let me think about this. How does this work? So we need this. Essentially, what's happening is the magnetic field is causing electrons to move, which is causing an electric current. And the reason that you can heat something up, something like a metal up, is that the electrons move fairly easily in the metal. So when you have a certain amount of force that's moving the electrons, you can get the electrons to move. And as the electrons collide as they lose energy, they transfer heat to the metal, and the electrons kind of never get started moving in something that isn't something that isn't a metal, or something that isn't an electrical conductor. I'm going to punt on this slightly, and maybe we'll come back to this one. It's always, as I say, always suspicious when a question seems like it's going to be easy. All right, we have another physics one here from Cap. How does a shortwave radio signal go completely around the world? So when I was a kid, I had a radio and it had different frequency bands, and some frequency bands in like the early evening, you would be able to hear radio stations that were significant parts of the way around the world. What happens is that, so normally when you just have a radio signal, it will just like so radio is a form of electromagnetic wave, just like light is a form of electromagnetic wave. Radio has a much longer wavelength than light. With light, you shine a light, there's the light can go, if it's just going through something transparent like air, the light just goes essentially in a straight line. And if you can see the light, so to speak, then the light gets to you. If you can't see the light, then the light is blocked. So it's kind of line of sight transmission from the source to the receiver. Now, it gets a little trickier because of the phenomenon of diffraction. If you have light is ultimately a wave, although its wavelength is very short. Radio is also a wave, but its wavelength can be a lot longer. What happens in diffraction, if you imagine a bunch of, let's say, water waves, and the water waves are getting to, they get to, let's say, imagine you have a whole line of parallel water waves, and they get to sort of the entrance to a harbor, let's say, and they're blocked. So some part of that parallel line of water waves gets stopped. Only the middle part, let's say, of the parallel line of water waves gets through. So now the question is, when you have that parallel line of water waves just going all in one direction, and you block out part of that parallel line of water waves, does the stuff that's in the middle that gets through, does it just go in a straight line with those water waves just keeping on going as they were going, and not, does it just go as if it was sort of a shadow from the walls, so to speak, and just keep going like that, or does something different happen? Well, the answer is something different happens. The thing will spread slightly as it gets past, when it gets through past the wall, instead of just going out sort of as if the thing was shadowed by the wall, it will spread out from the sides at a certain angle. Why does it do that? Essentially, the way to think about it is that there's a thing called Huygens principle, which basically says that when you have something like a wave, you can think of things, you can think of kind of the source of making a wave as being every point on the wave is sort of making a new piece of wave. And every point is making kind of a circular piece of wave. It's like you drop a stone somewhere and you'll see these circular waves produced. Well, as you form waves, every piece of wave is forming new wave in that same kind of way. Like it's making a circular area of wave. But when you have those circular areas of wave all being made at all the different points on this plane wave, on this parallel collection of wavefronts, when you do that and you add all those things up, you just get another parallel wavefront. But you don't get that when the thing was blocked. Instead, a piece of this kind of circular wave can still sort of keep going because there was just no other wave, that there was nothing else there. There's no other source of wavelets, so to speak, outside of that region which hadn't been blocked. And so what will happen is a phenomenon called diffraction, where you get a sort of a spreading, where you get waves that go that go off at an angle away from the place where sort of the pure kind of following the rays kind of propagation of things would go. So in general, the amount of diffraction depends on the wavelength of what you're dealing with. And typically when you have kind of an opening that is kind of comparable in size to the wavelength, the distance between the wavefronts, then there will be there'll be more diffraction. And when you have an opening that's huge compared to the distance between wavefronts, the amount of diffraction, the diffraction is kind of by about one wavefront in direction, so to speak. And so if the kind of opening is huge compared to the distance between wavefronts, it will not be a significant effect. If it's small compared to the distance between wavefronts, it will be a big effect. So for light, we have to go down to the scale of billionths of a meter and things to get to the point where we have significant diffraction effects. For radio waves, because the wavelength can be much longer, diffraction is a more significant thing. So that means that when you have transmission of radio waves, for example, for cell phones and things, diffraction is a significant effect. it is not the case that the radio waves are just going purely in a straight line. If they hit an obstacle, there will be some diffraction around that obstacle. So in a sense, you get to see a bit around corners that way. Okay, so that's sort of what normally happens is radio, except for diffraction, radio basically is just going in a straight line from source to receiver, just like light does. But now the issue is that happens so long as there's nothing that acts as a mirror. If there's something that acts as a mirror, as we know from light can hit a mirror and bounce off. And so like you can think about the photons in the light, the little particles of light, or the wave that corresponds to light. Light behaves both like a stream of photons and kind of like a wave. That's another story about how that sort of those two complementary views of light work together. But either way, what's happening is we can think about it like particles, like photons. The photons hit the mirror and they bounce off, just like a billiard ball will bounce off the side of a table or something. And what's happening is, and so what typically happens is, what causes a photon of light to bounce off something as opposed to just to get absorbed? So for example, you shine light on some I don't know, piece of black paper or something, the light basically just gets absorbed in the black paper. You shine light on a nice polished piece of metal, the light will typically be reflected like a mirror. Why does that happen? Well, what's happening is that when the photon hits the material, what it's doing is it's getting absorbed by an atom in the material. So the photon hits the atom, it causes the atom to go into a higher energy state. And the atom then, after a short time, will decay back to its low energy state and it will re-emit a photon. So in other words, there's a photon that is being, that when the photon hits the material, it's causing something about the material to just absorb the energy of the photon, and then the material loses that energy by re-emitting a photon again. So the question is, how easy is it for the material to do that? So there are fundamentally two so-called dielectrics, materials that don't don't conduct electricity, and conductors like metals that do. And so the way that works is, in a conductor, well, the electrical current is a bunch of electrons flowing from here to there. In a metal, there are lots of electrons that are just sort of hanging around. So the metal, the metal is some array of atoms, and each atom has some electrons associated with it. And the question is, do the electrons that are associated with different atoms, are they tightly bound to each individual atom, or are the electrons kind of a shared sea of electrons shared between all these different atoms? What happens in a metal is that the electrons essentially, in a sense, the atoms are sort of close enough together and the electrons are far enough away from their nuclei and so on, that you get this kind of whole sea of electrons, where basically the electrons, instead of being very much attached to one particular atom, can kind of float freely through the metal. And so the result of that is, it's much easier to get to change the state of an electron. It's a much lighter object, among other things, than it is to sort of change the state of an atom, or rather it's easier for when you have a photon that interacts with a metal, what it's interacting with is electrons in the metal initially, and it is much easier for the photon to get re-emitted to sort of get re-emitted in such a way that it bounces like a mirror. There's a little bit more detail to how that actually works, but in rough terms, it's kind of how easy was it for the photon to get absorbed and re-emitted sort of quickly by the material, and to what extent did it kind of go into the material, get absorbed by an atom, and then the atom sits around and thinks about it and eventually re-emits the electron, or re-emits the photon, or perhaps even doesn't. Perhaps what happens is that the atom just goes into this, perhaps it emits a different photon, not one that was just like the photon that came in. In any case, that's how things work with metals. Normally, in the atmosphere, we have the atmosphere doesn't conduct electricity. The air is a pretty good insulator. When we put enough voltage across the air, eventually it will transmit electric current through breakdown of the air, and that's what lightning is, for example. What is breakdown of the air? What's happening is that when you're trying to push an electric current through the air, mostly the atoms just have their electrons firmly attached to them, and the electrons aren't moving anywhere to make an electric current. But if you push them hard enough, the electrons will get stripped away from the nuclei of the atoms, and they'll be able to do kind of like what happens in a metal, and the electrons will be able to sort of move. And that's what happens in a lightning strike, is that there's enough voltage that it's kind of pushing hard enough. The electric field associated with is pushing hard enough to push the electrons out of atoms and to have them start moving sort of from atom to atom, so to speak. And you're forming, when you sort of rip electrons away from their atoms, you are forming a plasma where you have like it happens in fire and things like that, where the electrons are no longer where again you can have something a little bit like what happens in a metal, where the electrons are much more free floating than they normally are, sort of normally, and they're sort of attached to the nucleus of an atom. So what happens is in the Earth's atmosphere, there's this thing called the ionosphere. The ionosphere is a region of the Earth's atmosphere high up. How high is it? It's probably, it's higher than planes fly for sure. But it's in the very, very outer part of the Earth's atmosphere, has the feature that what's happened is, as a result of bombarding with ultraviolet light in particular, I think that's the primary thing that does it. The atoms have the atoms of oxygen and nitrogen and so on in the air have their electrons kind of stripped away from them, and that causes them to act as a plasma, and the electrons are kind of free floating. And when the electrons are free floating like that, it behaves much more like a metal, and in the sense that it can reflect electromagnetic waves much like a mirror would reflect them. And so what's happening in shortwave radio is that you are seeing the radio wave hits this thing. It's called the Appleton layer. It's part of the ionosphere, and it hits that. That is sort of behaving like a mirror of radio waves. It bounces back down and then keeps bouncing. Now, actually, an interesting question is, why does it bounce back an additional time from the Earth's surface? I am actually not sure. Maybe if it's water also, well, I'm not sure how that works. For sure, you can, one bounce is easy to understand, but I think maybe there are additional bounces within the ionosphere. I think that's right. I think that's what happens. That once the radio wave, so the radio transmitter is transmitting this radio wave, the radio wave is going in all different directions. Some of that radio energy gets up into the ionosphere. I think it bounces around there, and it kind of keeps bouncing there, and that means that it can sort of go around corners around the Earth, because it's kind of bouncing in this thing that's kind of like a waveguide, where it's where the radio wave just keeps bouncing there, and eventually enough of it sort of gets out at the other end, so to speak, that you can detect it, even if you're far away from the original source. All right, so that was my attempt at describing shortwave radio. And by the way, the question of why, so this phenomenon of whether it can bounce or not depends on, it's the same kind of question as, do you have a material? The material might be, it might look red, for example. What does it mean when something looks red? What it means is that if you illuminate it with white light is a combination of all different colors. It means that if something looks red, it means that it is reflecting red light back to you and absorbing other colors like blue light, for example. And so in general, this question about what colors get reflected, what colors get absorbed, is a question that's in the language of physics, that's the imaginary part of the refractive index. So refractive index tells you things about how light gets transmitted through a material. It tells you the real part of the refractive index tells you how much light is slowed down as it goes through a material. So for example, in water, it's about refractive index about 1.33, which means that light is going 1.33 times slower. Why does that happen? It happens because the light is going through the water by being absorbed by an atom, then the atom re-emits it. But there's a short delay before the atom re-emits it. And it's that delay that kind of slows down the transmission of light in water. And it does that by a factor of 1.33 for water. For glass, it's like 1.5, et cetera, et cetera, et cetera. Diamond, 2.7, those kinds of things. But the way that one sort of describes it in electromagnetic theory is to say that in addition to the real part of the refractive index, which is slowing things down, there's also an imaginary part, and it works that way because of its e to the I times the frequency times time and so on, and times the refractive index, and that if the refractive index has an imaginary part, that is a decaying exponential type thing. But the point is that one then has the idea of that there can be both something where the absorption depends on the color of the light and this refractive index can depend on frequency. So for example, it can be the case in some materials, red light goes faster than blue light and so on. That's how things like prisms work. That's how they split the colors of light, is because one color of light is going faster, so bends more or less than another color. But so similarly, there's a variation in the amount of absorption that happens depending on the frequency. And so the same is true with the plasma. There's a whole plasma dispersion function, it's called, that has to do with what frequency of radio will be absorbed or transmitted in what way by a particular kind of plasma. And that's the reason that radio waves of some frequencies can successfully get reflected by this layer of the ionosphere, and others cannot. Now, another question, which I should know the answer to and don't immediately, but let me think about this for a second, is that the best time, I think, for shortwave radio is like early evening, I believe. And I think the reason for that is it depends on light from the sun producing this effect in the ionosphere, and probably a little bit more thought we could figure out why the early evening is the best time for that. All right, let's see. Let's try something else here. Oh, so many other questions. Okay, there's a question from Ernesto. Will new logical mathematics operators be invented or discovered? So we talk about, I'm not sure necessarily what one means by logical mathematics operators. Things, when we talk about, in logic, for example, we'll be typically talking about, P or Q, P and Q. If P is a proposition that says, it's raining today or something, and Q is a proposition that says it's raining tomorrow or something like that, we can say P and Q, and that represents that combination of logical statements. Now, when you ask what are the different possible combinations, if you have two possible truth values, true or false, it's not hard to work out that there are just 16 possibilities. For if one thing's true, the other thing's false, then the result might be true. And if they're both true, the result might be false or whatever. There are only 16 possible cases. Many of them, but not all of them, have names. And says if they're both true, then it's true. If either of them is false, then it's false. Or says if either of them is true, then it's true. Only if both of them are false is it false. But there are more exotic ones like NAND, is if it's the not of the and of the two things. And there are different possibilities. There are different kind of truth tables you can make where you're saying, given that this is true, that's false, and so on. There are there are, let's see, there are 16, well, there are 4 possibilities for saying the first thing is true, the second thing is false, the first thing is false, the second thing is true, and so on. There are 4 different cases: true, 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 false, false, true, false, false. And for each of those, you have to say, is the result going to be true or is it going to be false? And there are 2 to the 4 or 16 possible ways to do that. And as I say, some of those things have an easy kind of interpretation in our language, like and or and things like that, and others do not. But that's kind of a very complete thing where we kind of easily enumerate what the possibilities are. Now, if we start saying we'll include not just true or false, but also maybe, and we'll make up some kind of calculus for 2 maybes, maybe and maybe makes maybe, and so on, then we can have so-called multi-valued logic, and then there's many more possibilities. But that's kind of a pretty complete setup. Now, when you talk about mathematics, there are things that you might do with numbers, like you say, well, I'm going to add 2 numbers together. Great, okay, that's plus sign, we're all good. We can, if you iterate adding numbers together, you get multiplication. Okay, we understand that. You iterate multiplication, you get powers and so on. These are all well understood kind of operators that combine numbers. But if you've got 2 numbers, there are all kinds of crazy exotic things you could do with those numbers. For example, one thing you could do is you could say, let me take the 2 numbers, let me reverse the digits in one of the numbers, and let me add the corresponding digits with the other number. That's a totally weird operation. We don't have a typical name or notation for that operation, because that operation is something that's kind of amusing to look at and it does some wild things, but it's not an operation that we generally find useful. So when you have something like numbers, there are certain operations that seem to be things that are useful in our world to do with numbers, and there are others that don't seem so useful. You can kind of grind the number up in a variety of different ways and sort of do operations on its pieces, like its digits, for example, and that's kind of a thing that doesn't seem to correspond to things which are kind of useful in everyday life. Now, occasionally, there are exotic uses for things like that question of taking a number and reversing its digits. You might say that's a useless thing to do. It's actually in things called fast Fourier transforms. That's something that is part of how one hooks up, how one decides how to combine data together, is all based on doing things like reversing the digits of numbers, although that isn't a normal kind of operation. And in general, if you just say, given numbers, could we invent a bunch of really exotic operations that will work for any pair of numbers, but then the answer is we can invent an infinite number of those kinds of things. A question is, which ones will be useful to us? I think that's actually a fairly deep philosophical question, because I think it has to do with how do we typically experience the world? What kinds of things do we think are important in the world? Let me give an example. There are cases well, let's see. There are phenomena. Let's see, what's the simplest case of this? There are phenomena in physics where you do get to kind of grind up the digits of numbers to some extent. So a typical case of that would be something like this. Imagine that you are, well, let's see. The most common thing is a thing called Cantor set, fractals. These are all related. And essentially what's happening is you say, I'm going to try and decide, I'm going to color things black or white. And maybe I just say it's half black, it's half white. Okay, that's straightforward. But maybe I do something where I nest different areas. Within this area of black, I'm going to have an area of white. Within the area of white, I'm going to have an area of black. And I keep nesting this. I keep on nesting that. So I get these tiny little areas where it's white, and tiny areas and areas where it's black. And I have this kind of hierarchy of progressively larger areas where it's black or white. That makes a typical kind of nested or fractal pattern. And if I ask the question, at any given point, am I going to get black or white? The answer to that question may depend on some digit in the number that represents the position of that point. So a fairly typical thing to do is, for example, you might say digits in base 10, and you might say, if the number contains any threes, sevens, or fives in its digit expansion, a point, 1, 2, 1, 1, 7, 2, 4, 6, 4, et cetera, et cetera, et cetera. If that digit expansion contains any threes, sevens, or fives, let's say, then don't allow that number. And then ask the question, what do you get if you do that? The answer is you'll get this complicated nested pattern with all kinds of little tiny dots of, pieces of white and black, if black is numbers you allow and white is numbers you don't allow, and so on. So that's a case where sort of where if you have that kind of nested behavior, then that's a way to sort of get something which depends on weird features of numbers. How do you get nested behavior? Well, for instance, if you have anything that's a branching structure, whether it's a tree branching or whether it's the kind of pathways in our lungs branching or any of these kinds of things, when you have any kind of branching structure and you say, what's the end result of all that branching? You will get something that's this kind of nested structure where these kinds of things would happen. So there are cases there where you can imagine other kinds of ways to process numbers that are rather different from the kind of usual arithmetic kinds of ways to process numbers. Ways to process numbers where it matters whether there's ever a 3-digit in the number, even arbitrarily far arbitrarily sort of low order place, so to speak. So, but I think this question of what is it that our senses notice about things like numbers, that's something where we notice certain kinds of things, but we don't notice other kinds of things. And insofar as we're interested in doing operations on numbers that are about things we notice, that's why we end up with these fairly small number of operations that we've been doing for 4,000 years at least, that are typically on numbers until you get to sort of higher questions in mathematics. Actually, we have another related question here from Elgiz. Why do we have two different kinds of things? Numbers plus operators, data plus algorithms. We represent many things with those things. Why not 3? Why not 4? Why not 1? Okay. So often when you think about doing things with computers, you think about there's just data. It's just, I've got a number, it's sitting there, nothing's happening with it. And there's also algorithms where you're doing things on the number, you're adding numbers together, you're doing operations. So it feels as if there's two very different kinds of things. There's data that just sits there, and there's algorithms that sort of process things and change them. Well, I don't think they're quite as different as that. If you even think about how the computer works inside, that number that's just sitting there in the memory of the computer, it's actually continually being refreshed. So you can think of it as, well, there is actually an operation going on for that data. It is like an algorithm. It just happens to be a rather trivial algorithm where all the algorithm does is to copy what it had before. And that's the way that kind of you propagate that number through time. So I think that the idea that there's sort of a sharp distinction between that which is just sitting there as data and that which is algorithmic and being processed, that isn't really such a sharp distinction. Actually, interestingly, in our theory of physics that now, one of the things that we realize is that the whole structure of the universe is based on this sort of giant network of kind of atoms of space. And what's happening throughout time, the progress of time, is associated with a series of kind of update events that update this giant network. And so, in fact, there wouldn't even be a notion, there wouldn't be anything, that the fact that there's anything that seems persistent is not trivial. It's at the level of sort of the atoms of space, things are continually being rewritten, maybe 10 to the 100 times per second. Very, very rapidly, things are being rewritten. Anything that sort of was a piece of the structure of the universe 10 to some trillion of a second ago is no longer a piece of the universe. It's no longer exists. It has been replaced by a new version, by a new thing. And so the idea that there's data that gets preserved, that has to be something that is a sort of a bigger feature of the system, not just the individual sort of atoms of space. And the way that works is much like, I don't know, in a water wave or something, there's this wave that kind of undulates on the surface of the water, but the individual molecules of water are not, that the wave is something that is sort of a collective effect of many molecules of water. The individual molecules of water are not what's moving when the wave moves, and so on. And so it's the same kind of thing with effects in space and in the fundamental physics. And so I think the way to think about kind of data versus algorithms is it something where you can recognize that it is persistent, that it is basically just, oh, that's that same number 2 just getting copied, versus is that something where it is obviously changing? And there are certainly plenty of examples where you could imagine that what it means to be, quotes, data is a little bit non-trivial, because it could be the case, for example, let's say you've got that number 2 and you say, okay, it's a 2. That number 2 is lodged somewhere in the memory of your computer. Okay, the way your computer operates, it might decide, oh, I'm going to move that 2 in my memory. I'm going to, and then the question is it the same 2 when it got moved? Is it just data? Well, actually, at the level of looking at the detailed operation of the computer, it's sort of a different 2 because it got moved to being stored in a different part of the computer's memory. And the question is, so in a sense, I think it's fair to say that sort of in some sense, everything is algorithms. Everything, it just happens that some algorithms are trivial and just the identity algorithm that's just copying things. So I think that's the sense in which, so in some sense, there is only one kind of thing, which is the continual updating of things by virtue of algorithms, but that updating might lead to no change of the thing, and then we just call it a piece of data. Yeah, so I think that's the answer to that, and that there really isn't a sharp distinction. Now when you are dealing with kind of low-level programming languages, then because of the way computers are constructed, they have a habit of being set up to have to really separate out there's just memory here that's just keeping data, and there's an arithmetic logic unit in the CPU or something that's processing data and making changes to it. That is really a feature of the details of how computers have been made for the past 60, 70 years or so. That isn't a fundamental feature of how things have to be. And in fact, there are certainly idealized models of computation, and perhaps more than that, when we get to have molecular scale computation, I suspect that the let's maintain the data thing will be much more algorithmically non-trivial than it is in the way that we at least idealize computers to work today. So I think that's kind of the way that works. Now, in something like mathematics, it's an interesting case as well. In mathematics, we sometimes identify functions, variables, those kinds of things as different kinds of things. That is, I think, a feature of kind of the way that mathematics and algebra and so on evolved. As we look at more abstract versions of mathematics through mathematical logic, and more so the kinds of ways that I built sort of computational language structures and so on, you stop seeing this sharp distinction between a function and a variable. For example, in Wolfram language, if you say the function f of x, there's really nothing different between the f and the x. You could as well say the function f of f. You know, it's a function of a function, you know, function where the thing that it is being applied to, the variable it's being applied to, is just the same kind of thing as the function. And in general, in our computational language, this idea of the functions, the data, the programs, the data, they're really all the same kind of thing. They're all represented symbolically by these expressions that have a certain structure and that ultimately refer to symbols. These symbols could represent a function like plus, but they could equally well represent a thing like the entity New York City, for example. There's no distinction between the function plus, it's just a symbol called plus, and the symbol that says, I don't know, something like now, the current moment in time. Those are just those are just symbols, and you can manipulate them as symbolic things, and there's no real distinction made between them. And that's, I think, a good way to think about kind of this sort of merger of, how do you break up computation so we humans can understand it? You don't need to break it up by saying there's separately a function and an operator and its operands, a thing that's doing the operation and a thing that's operating on. That distinction is not necessary. That distinction might be useful for some ways of thinking about things, but it's not a necessary distinction. And it's not even the way that in our computational language that things are implemented. It's like those two things are the same kind of thing all the way down. Let's see. Okay, there's more of a history question about Norbert Wiener. Let me move that to my history of science and technology question. The basic question was, do I know about Norbert Wiener's work? Yes, I do, quite a bit. Is it relevant to current computer science at all? It was primarily oriented around this area that got called cybernetics, control and communication in kind of animals and machines type thing. And cybernetics led to control theory, it led to various kinds of things. It has not been as directly relevant specifically in computer science, although perhaps one could draw lines between that kind of approach and what's been done in modern machine learning and so on. Maybe I can talk about that more in a history discussion. Okay, there's a question here. Oh gosh, all kinds of things. Okay, there's a question from Erin. What's the difference between CPUs, GPUs, TPUs, ASICs? Okay, a technology question. All right. In our computers, there is a central processing unit, a CPU. That's the place that kind of does the work of doing the computations that our computer is doing. And the way that work is getting done is any program on our computer is eventually represented as machine code. What is machine code? Machine code ultimately says there is this instruction that will be done to this data, for example. And for example, one of those instructions might be, add these two numbers together. Those two numbers, they are located at this location in memory, that location in memory, go fetch the data from those locations in memory. And then inside the CPU, the operation of the CPU is let's add those two numbers together, which means those numbers are both represented as sequences of bits in binary in our computer. And the addition consists of, well, doing the same kind of thing we would imagine doing if we were doing it by hand. You're just adding the digits, doing carry bits, all those kinds of things, and then getting the result. So in a typical computer, there are some number of tens or hundreds of fundamental instructions that the computer knows how to do, like adding numbers, like copying a piece of data from here to there, like setting a piece of memory that might be connected to your screen to have some particular value so that some pixel on your screen will light up, those kinds of things. And there are some number of so-called opcodes, some number of different intrinsic instructions that are built into the operation of the computer. And so when a CPU is made, it's this microprocessor, this chip that might have, hundreds of millions of transistors on it that are implementing circuits, which in the end will be the things that opcode 73 will be, subtract two numbers. And whenever the program contains opcode 73, that particular part of the circuit that is the microprocessor that makes your CPU, that it will go to that particular part of the circuit and it will say, okay, run this data through this part of the circuit and get the result from opcode 73. And usually there's some, it's called the decoder tree, where you're basically taking the opcodes, which are themselves represented as numbers, and you're saying, okay, this is opcode 73. That means I'm going to take the data that's being used for this opcode, I'm going to shuttle it off to this part of the CPU, I'm going to do the operations that correspond to the circuit in that part of the CPU, I'm going to get the result back and keep going and executing the program. So in a CPU, the typical story is over the course of time, people have invented a collection of opcodes that they find useful. There had come a time when people had hundreds and hundreds of different opcodes that would do very complicated things, like would evaluate polynomials. They would do all kinds of things that were very, very ornate operations, and those things were burnt into the hardware of the CPU chip. So in addition to adding numbers, it might be evaluate a number x squared plus 1. That might have been one of the opcodes in the CPU. In the 1980s, there was a big movement to make so-called reduced instruction set computers, where the idea was actually have a much smaller number of operations, of intrinsic opcodes that the computer knows how to do, because anytime you're computing x squared plus 1, you can always do that by doing a series of other operations. You do x times x plus 1. That will be a series of sort of lower level, simpler opcodes. And so what people had done, people had originally thought, oh, if we burn into the hardware computing x squared plus 1, if we make a circuit specifically for that, it will be a more efficient way to do things. The idea of reduced instruction set computers, RISC architectures, was actually just implement a much smaller number of opcodes and do it incredibly efficiently, and then leave it up to the compiler, leave it up to the program that takes the code you write and turns it into machine code to figure out a really good way to get the best machine code so that you can do these operations. And the main thing that happened was that it was realized that you could, with the compiler, with the arrangement of exactly what kind of instructions do you want to make, exactly what sequence of instructions do you want to make in the machine code, the compiler could be really smart about optimizing exactly which series of instructions were done to achieve this operation. Because typically when you work something out, let's say, I don't know, x plus 1 times x minus 3 or something, that's a bad example. Any kind of computation, there are typically many ways to get that result from the computation. If you say, how do I get that result by doing this series of elementary operations, there may be many different programs, many different sequences of those elementary operations that will always give the same result. It's kind of like a mathematical theorem that says, x plus 1 times x minus 1 is equal to x squared minus 1. You could use that theorem to have two completely different ways to compute the same result in your computer. And so if you know exactly how long each operation is going to take and so on, you can essentially write a piece of software that will say, given this operation that I want to do, let me find the best way to get that operation done from a series of machine instructions. And so that was kind of the approach of which is now really the dominant approach, is keep the number of burnt-in machine instructions, the opcodes that the CPU really understands, keep that rather small, and have the compiler be clever about figuring out exactly how to take the code you have and write it in terms of those machine instructions. Okay, so now that was kind of idea number one. You have the CPU, it has certain instructions in it. Now people over the course of time are always saying, but we have this particular operation we just want to keep on doing over and over and over again. And we could write it to be done by a series of machine instructions in the CPU, but actually we can make a piece of special purpose hardware, a special circuit that does this operation much more efficiently. So back in the 1980s, for example, it was very common for the CPU of a computer not to have the built-in capability of doing floating point arithmetic. So it could deal with integers, whole numbers, but if you had the number 3.7, it wouldn't know how to deal with that number with a decimal intrinsically. There would be software that would allow it to know how to do that in terms of integers, basically, but it didn't have a way in the circuitry of the computer to deal with those numbers that have decimal points in them and so on. So what happened is people introduced these things called FPUs, floating point units, which were special purpose hardware, which just had a bunch of extra instructions for dealing with these numbers with decimals. So gradually what happened is FPUs gradually got absorbed onto CPUs as people figured out how to build CPUs with bigger and bigger circuits in them, more and more transistors in them, and so on. It was like, well, let's just put an FPU right on the CPU chip, and then let's kind of merge the FPU into the CPU. So it was no longer the case that there were these extra, it used to be the case that there would be these extra instructions. And for example, a compiler that was taking something in let's say C code, C language or something, ultimately in Wolfram language, it would be something which is primarily going from our top level language down to sort of interpreting that top level language in terms of machine instructions. There will be a question. If your computer happens to have an FPU, then say, okay, we can use these extra machine instructions to do certain floating point operations really fast. So that was kind of a big kind of idea of have this coprocessor, this FPU that went alongside the CPU with extra instructions which your programs could make use of. Now, what happened with FPUs is typically when you compile a program, when you take it from, let's say, C language code down to machine code, then you would be able to set an option in your compiler that says, I've got an FPU. You can generate FPU instructions as well as CPU instructions. Okay, when the FPU got kind of included in the CPU, that no longer was an issue, and it all got a bit simpler. Okay, but now there are other operations that people often want to do. And so people gradually kind of, well, actually, let me address two pieces here. So there are, okay, what if there's a particular operation you just want to keep on doing? You've got some video encoder, and it does some particular series of instructions where you're taking arrays of numbers and doing this and combining them in that way, et cetera, et cetera, et cetera. You always want to do the same thing. You say, that's a real waste to do it in software where I've just got this series of machine instructions and I'm doing it like I would generate from a compiler and so on. So there's this notion of microcode. This was a common thing. It's not so common these days, actually, where, okay, so normally when you execute an instruction in a CPU, there is, at least in a rough approximation, and it's gotten a little bit more complicated in modern times, you're doing one opcode at a time. You add the numbers, you subtract the numbers, you multiply the numbers, et cetera, et cetera, et cetera. But actually, if you look at your CPU chip, there's one area of the CPU chip that's dealing with adding numbers. There's another area that's dealing with multiplying numbers. There's another area that's dealing with, I don't know, saving things in memory. There's another area, et cetera, et cetera, et cetera. There are all these separate areas of the CPU. And normally, if you're running a program, it's just one opcode at a time. One area of the CPU is being used at a time. But if you want to be really, really detailed, and you really know how your CPU is set up, you could set it up so that actually, when you have addition going on here on one side of the CPU, you have multiplication going on here on another side of the CPU. So there's this idea of microcode, which is the idea of having something which says to the CPU chip, it says, I want you to do exactly this kind of thing, where you've got, it's not just the series of opcodes that are sort of centrally decoded opcodes. It's like, have one part of the chip do this, have another part of the chip do that, and so on. And so what's quite often done is to write, and I guess this is done for some of the important libraries for doing certain kinds of matrix operations, things like this. They're written at the level of, well, we know exactly how the chip is set up. And so we can say, get this side of it to do this while this side of it is doing this. And you can make it more efficient than if you just do everything as opcode, opcode, opcode in the main part of the chip. Okay, so that's a way that you can sort of improve the performance within an individual chip, but you have to know a lot of detail about how the chip works. Another thing you can do is just make your own chip. You can say, I just want this particular piece of circuitry. I'm going to just keep doing it over and over again. Let me just make a chip that only has that particular piece of circuitry. That's what an ASIC is, an application-specific integrated circuit. So in that case, what you're doing is you're creating in the most extreme case, you're just saying, I want to make this particular circuit, and I'm going to make a chip that's based on this particular circuit, and I'm going to just manufacture a new chip, and all it does is a piece of video decoding. It doesn't do general purpose computing. It's just intended to do video decoding. Now, there's a thing in the middle of that, things called FPGAs, field programmable gate arrays. And the idea of those is that you have something where you have sort of a standardized collection of different kinds of operations that you can be doing, and you can kind of make your own circuit by kind of hooking those together in different ways. So you have a big sort of piece of silicon or whatever that has this whole array of different sort of cells that do different operations, and you get to sort of define what the wiring is between those parts to define what operations you want your sort of semi-custom built chip to do. And that's a very common way to make ASICs in modern times is these FPGAs. Okay, what is a GPU? Well, back when people got really serious about doing graphics operations for video games, for video encoding, all these kinds of things, it became, there were these particular operations, and the most common issue is you've got a whole array of numbers. You've got an image which has a whole bunch of pixels in it. You've got a something like that. You just want to do the same operation to all those pixels. And if you were doing that in a standard CPU, you would have a series of operations where you say, do it to one pixel, move another pixel in from memory, do it to that one, move another pixel in from memory, do it to that one, and so on. But instead, you want to do these kind of vector operations where you say, I've got this whole array of pixels, a whole array of values. I just want to do the same thing to all of them. So what people started doing was making special coprocessors, GPUs, graphics processing units, which would have vector instructions, which would have things where you would say things like, I want to do this particular operation on this whole array of numbers all at the same time. And so typically in a GPU, there'll be some set of these kind of big registers, big things where you can keep arrays of numbers, and then you just do that same thing to all of them. And it's kind of an art to make up the right kind of instructions that are the useful instructions that are the right building blocks to do, let's say, video encoding or something like this. And over time, those got invented. A good friend of mine is involved in making up many of those kinds of instructions for what have become sort of the common GPUs. It's something where it is, you're making up a particular kind of operation. Is this thing that does a particular kind of rearrangement of the elements in this array of numbers, is that useful? It's quite similar to the process of language design of saying, what functions should we build into our computational language, but it's a much lower level version of the same kind of thing. So what happened with GPUs is they have these particular operations, these particular instructions. Now, they don't play as nice with, for example, when sort of the main operations of your computer, the things controlled by your operating system and so on, those are, the CPU is what does all of that stuff. The GPU is something where there are particular pieces of computations that you say, that will be really good if that was done in the GPU. Now, typical programs, you have to do special work to make use of the GPU. And there are different languages, different libraries and things that you use to say, I'm going to make a piece of GPU code. It's not your generic piece of code that gets compiled into GPU language. That isn't the way it works. It's beginning to work more like that. I have to say, I thought sort of in the evolution of engineering that the GPU capabilities would gradually get absorbed into CPUs. That hasn't quite happened yet, although some pieces of that have happened. But so GPUs tend to be optimized for this sort of parallel operation, on these many operations done in parallel across a sort of whole array of data. So then there's TPUs, which I think TPU is probably a Google name for this idea, but it's basically making sort of semi-special purpose chips that deal with the kind of operations that are common in neural networks for machine learning and so on. Those operations are actually built on the same kinds of operations that are done in GPUs, the same kinds of operations that are done in one of the things is there's a lot of operations that are on arrays of numbers, on matrices, linear algebra, etc. Those kinds of operations are important for computer graphics. They're also important for the way that neural nets are set up, these with the way they're set up right now. And so, but there are particular sort of variants of that that are things that you can build special purpose hardware to implement, and that's what people have been doing. The various different companies have various technologies for this that are sort of special purpose neural network chips that are specially optimized for those kinds of things. Now, it's a complicated trade-off, because the same thing that happened in RISC architecture, people had said, oh, we want to get this particular operation to go faster. Let's burn that into the CPU. Let's spend a lot of effort building up a circuit. Let's, but then our whole CPU might run slower because we have to have this extra piece, and we've got to deal with the fact that there's some timing set up here or there. It would be much better to have a sleeker, simpler CPU. That was kind of the RISC idea, and to kind of have the software assemble the right sort of sequence of operations to be done. Whether that will happen in the world of neural networks and so on, I'm not sure. I think it's quite possible it will happen. What the trend right now tends to be more, let's put these very complicated things and burn them into hardware. Now, of course, there's a bunch of trade-offs here, because as the hardware gets easier to make, you know, the billion transistor CPU chip, as people figure out how to make very, very tiny transistors, you know, that are I don't know, 5 nanometers across or whatever else it is, as people figure out how to make much smaller components, you can put more transistors, more detail of circuit on this chip, and it becomes less of an issue to say, oh, let's build in this special weird thing that does this particular kind of operation that's needed in this exotic kind of neural net. It's like, why not? We can put another 100,000 transistors on this chip, no problem. It's not going to cost any extra. But as it depends on the engineering trade-offs, whether it's a better idea to say, no, let's keep our chip really sleek and simple, and let's kind of build up all the complexity on the software side. So that's kind of the idea of these different kinds of ways to implement. I mean, it's all about how do you actually make your computer compute, and in the end, any one of these things, the amazing thing about software is, and the amazing thing about universal computation is, even given one of these kinds of computational systems, it's always, at least in principle, possible to write a program for it that will do anything. So, for example, with our CPU, we can write a program that will do exactly what our fanciest TPU will do. There's a trade-off. It takes longer to run, potentially, because, for example, the program it's running different pieces, one after the other, sequentially, whereas if you knew more detail about how the chip was set up and you made these very fast pathways on the chip, you could run things in parallel and make them much faster. So there are these trade-offs, but in the end, the ultimate computations you can do, but for timing, are all the same. And in the end, timing tends to be driven by things like physical processes that are going on. You know, can the car figure out which way to turn, you know, fast enough to make a difference, so to speak? Or can we get this video fast enough that we humans sort of, you know, fuse the frames together and it looks like a continuous video, and so on. All right, I think need to go in a moment. Maybe I'll try one more question if I can see. Okay, a bunch more physics questions, which I'm happy to do. My gosh, there's a question about dogs and hearing loss, and I'm afraid that one I don't know offhand. I can make guesses, but I don't think that's what I should do. All right, I'll do one more. Okay, from Mar here. How viable is a big numerical reverse database to identify closed forms for real numbers, such as Simon Plouffe's inverter? Okay, this is kind of an interesting one, maybe. Okay, you've got the number 1.2736846. What is it? Where did it come from? You could just write it down, but it could be that that number is actually pi squared over 7. It could be that that number has a short sort of symbolic description. That number might be the square root of 2. We can write it very easily. Or that number might be something which we could describe as 1.414863424, etc., etc., etc. It's a number that just seems like a random number. So some numbers, a very small fraction of all numbers can be described easily. So for example, rational numbers like 2/3, 0.6666666 recurring, that's a definite thing. If we just change one of those sixes out at the billionth digit, that wouldn't no longer be 2/3, and we might have no particularly simple way to describe. If we just change one digit, there's a pretty easy way to do it by just adding 1 over blah, 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 but 1 over 10 to the blah, blah, blah. But if we monkeyed around with a bunch of digits out there, there might be no simple description of that number. So the question is, which numbers have simple descriptions? First thing to realize is the fraction of numbers that are rational numbers. Okay, so we have whole numbers and we have rational numbers, which are ratios of whole numbers. So, 3/4, 7/8, et cetera, et cetera, et cetera. A little bit of a trickiness with rational numbers already that, 4/6, which seems like it's a definite number, is actually the same as the number 2/3. That's that we can cancel the extra factor of 2. And so what we might think of, oh, you write down a number, any two numbers written down differently will be different numbers, but it isn't true for rational numbers. Even though those two numbers are written down differently, 4/6 and 2/3, they're actually the same number, they're equal, they're numerically equal numbers. And by the way, there's an even bigger trickiness, which is if we write down numbers as decimals, the number 0.9999999, 9's all the way down, is that number the same as the number 1.00000 or not? Those numbers can be arbitrarily small different. Are they in fact the same number? For most purposes of mathematics, those are the same number, even though their representation is different. And that causes all kinds of difficulty in understanding how real numbers which aren't just whole numbers, work. So the question is, I was going to say, if you ask the question, is every possible number a rational number? The answer is no. You can, when you have sufficiently many digits, any rational number is a ratio of two integers, and if the integer has, it's kind of a limiting thing. If we say there are an infinite number of digits, we can't get to the infinite number of digits with integers. It just doesn't work that way. There's more real numbers than there are integers. If you call the number of integers, it has a name. It's called Aleph-0. It's a so-called transfinite cardinal, is the number of integers. Now that number, you can't, like, I can't give you that number of M&Ms or something. That number is just a theoretical number. It's really an infinite number, but it's a particular kind of infinite number, Aleph-0. It turns out that the number of real numbers is basically 2 to the Aleph-0. Basically, you're for every there's a higher level of infinity that you get to that corresponds to the real numbers. So in a sense, that means there are many more real numbers than there are rational numbers. But so the question is, if you have a number that comes out of a calculation and you say, I wonder whether, and that number you got by some numerical computation method, and you say, I wonder, I've generated 50 digits of this number. I wonder whether actually that number is pi squared over 7, whether actually that number is something that can be represented in a simple symbolic way, where if I had been smarter about doing the calculation and had done it kind of algebraically rather than numerically, I would have just got the answer pi squared over 7. I wouldn't have got this big block of numbers. Okay, so the question is there a systematic way to say what's the number that, what given a series of digits, is it even close to a nice to describe number? Okay, the tricky part of this is there's this complicated trade-off. What's a nice to describe number? If this number was equal to to, let's say, 2 over square root of 3. That's like, okay, that's fairly nice. But it's also really close to pi to the 17 over 742 minus the zeta function of 5 plus whatever. You say, well, that's not quite so nice. And you say, I'd really prefer to get the 2 over square root of 3 form, even if that might be a little bit further away from the actual digits that I have, or might not agree for as many digits or something. But so there's this question of, can you assess what is what is the likely nice number that might have been the nice to describe number that might be close to this real number that you have. Now in Wolfram Alpha, for example, if you just type in some random number, it will try and tell you nice possible closed forms. Closed form meaning something where you can just say the whole thing. You can just say it's pi. You're not saying it's 3.14159 ... and you don't say the whole thing. A closed form is something where you just say there's sort of the symbolic representation of it as it's square root of 2. It's, pi to the power e or something. Now, how does one do that? Well, there is a trade-off. How exotic do the formulas get? How many terms do the formulas have? And then what kinds of things appear in the formulas? I mentioned 2. Okay, that's pretty communal garden. I mentioned pi. Okay, that's a little bit more exotic. I mentioned e. That's probably a little bit even more exotic. Let's say I mention the golden ratio. Let's say I mention the Catalan's constant. I could start giving you all these named things which have occurred in the history of mathematics, but they get more and more obscure. And so the question is, if I've got a trade-off, if I say, well, this thing is really close to Catalan's constant cubed over 6, it's also roughly square root of 3, which would you pick? Well, or actually worse, it's equal to Catalan's constant over 2, or it's this combination of 8 square roots. Which do you pick? You kind of have to have this measure of what is the sort of lowest information content thing. In other words, if Catalan's constant requires you to know all this extra stuff from the history of mathematics to know about it, that's kind of a higher cost than if it's a few more square roots. So actually in Wolfram Alpha, what we did is, when we're trying to assess the relative importance or relative sort of complexity of these different kinds of constants, let's say, we just searched the mathematical literature and we said the more frequently the thing occurs, the less obscure it is, and the lower the kind of cost of producing it in a formula is. But there will be cases where there's a very, very obscure constant, but you might really nail this result by using that obscure constant, but you could also get a good approximation by using a slightly more complicated formula with ordinary constants. So basically that's the idea, that you have to kind of have this way of weighting these different pieces that you could put into your formula and say which ones are more important than which other ones. From a technical point of view, I mean, we've done a pretty good job, I think, with the one of these in Wolfram Alpha. The difficulty is more of a philosophical difficulty of kind of how do you represent each one of these things that's the such and such constant is essentially a packaging of certain ideas in mathematics, where you say, and the result is such and such a function or such and such a thing, and you give that function a name. That's saying this thing, wherever it came from, we now know it as this particular name, and we can refer to it in that way. And it's a question of sort of what did you package in mathematics to provide in this form. All right. Well, we should wrap up here. Thank you very much for lots of interesting questions. I am duly humbled by my failure to nail our first question about induction. Maybe we'll come back to that another time. Thanks for all the interesting questions, and see you again another time. Bye for now.